Okay, so good morning, everyone. In the last class, that is in the last week, we are discussing about fine structure of hydrogen atom, and there actually we have seen that what are the origin of different corrections or different energy correction terms in the spectra. So one of the source of this correction was coming from relativistic effect, and the next one was spin orbit coupling. So that was the last thing which we discussed, I think, in the last lecture. Okay, so just a quick recap. So what we discussed was, so we talked about spin orbit coupling, and yes, so before that actually we talked about relativistic effect. So there actually we are, yeah. So this is that first slide where we started discussing the relativistic correction. So what we had there is that we had a correction term that is of the order of p to the power 4, and that perturbation we have found out that is the first order, basically the first order perturbation theory gives the expectation value of that energy term, and then we got some expression for that, and that total expression comes out to be En square divided by 2mc square times some terms within the bracket. Okay, and then we observe that the actual order of magnitude of this correction term is quite small compared to the energy level of the hydrogen spectra. So next we started discussing spin orbit coupling. So it is basically coming out of the source. I mean, the source of this effect is that since the electrons are moving in the magnetic field, and the magnetic field is being generated because there is a proton, which is also magnetic, that is present there. So one is moving, that is generating a magnetic field, and then other is kind of experiencing that. So it's vice versa picture. So we have actually calculated the magnetic field, and then we have got an expression for the field in terms of the orbital angular momentum vector, and then we had also looked at what will be the dipole moment of an electron that can come out under such scenario. So we have finally got a term like H will be equal to E square divided by 4 pi epsilon naught m square c square divided by 4 m square c square r cube s dot l. So these are all past few terms are constants, and only this s dot l term is actually giving out what is the interaction between the spin and orbital angular momentum. So s is the spin orbital angular momentum, and L is the orbital angular momentum. So here we talked about there is an extra factor too that is coming because of relativistic theory of Dirac. And then here actually there is another factor which of half which will come up, that is because of Thomas precision. So what it says is that the analysis what we have done so far was in the rest frame of an electron. So it was not an inertial system. It accelerates because it's moving, right? If that is the case, then we have to do some kinematic correction. So here we have not done, we will not be doing the exact correction, but you can look at this reference 12, which is basically this paper that I have written here. That is the same Journal of Physics. So if you are interested, you can look into this paper. So this correction has been explained nicely in that paper. So that actually gives us an additional factor of half. Okay. So if we take care of these two factors, then our total spin orbit Hamiltonian of a correction term will come out of this form, that is basically this expression HSO prime will be equal to E square divided by 8 pi epsilon naught times 1 by m square c square r cube times s dot l. Okay, so here one thing to remember is that basically here we had this factor which is 2 that was taken into account, and here also we had another factor that is half which we are taking into account. So altogether these two factors are not giving any additional contribution because 2 and half they are cancelling each other. Okay, so effectively we are ending up with the same expression of the correction, or let's say the Hamiltonian arising due to the spin orbit interaction what we started with earlier. Okay, so this is the expression. Oh, any question on this? Okay. So now what we have to do is that we have to find out the energy eigenvalue, or let's say the energy that is associated with this correction term. How will you do it? So the simple way is that we have to somehow simplify this expression. How will you do it? Okay. So here we have L and S. Now, as we know that, where is my pen? Okay, here. So here basically we have L and we have S. So these are basically spin and orbital operated here. Now they are not separately conserved. However, HSO does commute with L square and S square. And the total angular momentum we can write in this form. J will be equal to L plus S. So this is the vector sum. Okay, so we all know these things. So what it says is that HSO prime, it does not commute with L and S, which means that these are not good quantum numbers, but it does commute with L square and S square. Okay. So now what we can do is that now we'll make use of this expression 6.62. So here there are some text. If you want, actually you can read it. So now we'll just expand this. That means J square we will expand in terms of L and S. So that will be equal to L square plus S square plus 2L dot S. So that we all know, this is basically a very simple mathematical expansion. But now the good part is that psi, that is the eigenstate here, if we operate J square on that, then we will get an eigenvalue that will be H bar square times J plus 1. Okay, and psi will come out. And similarly, L square, if I operate it on psi, then I will also get some eigenvalue here, and also S square, if I operate it, then I will also get some eigenvalue. Now, what it does here is that I can express L dot S in terms of J square, L square, and S square. Okay, so if I do that, so in that case, I will get L dot S will be equal to this expression, that will be H bar square by 2, and within the bracket I will have J times J plus 1 minus L times L plus 1 minus S times S plus 1. Is there any question so far on this? Is it clear to everyone?
Yes, sir.
So how did you get that expression S square by 2 J little J plus 1?
No, can you repeat it again? Hello?
Sir,
can you repeat the question?
Sir, the eigenvalues of L dot S are, how did you get that?
Okay. So very simple thing basically. So you can see. Okay. So here you see I can write J square equal to L square plus S square plus 2 times L dot S. Is there any confusion on this expression?
No, sir.
That is clear, right? Okay. So now you see what we are trying to do here is that we are trying to find out some form of L dot S in terms of let's say some measurable quantity. Okay, right. So now L square, S square, and J square, these are the three operators whose eigenvalues I know already. Okay, so let's say if there is a quantum state, let's say if it is a NLM state of hydrogen atom, if I operate J square operator on this, then I will get this eigenvalue H bar square times J plus 1 times psi. That is clear, right?
Yes, sir.
Similarly, if I operate L square over psi, the eigenvalue will be L times L plus 1 times H bar square, and then psi will be here also.
Yes, sir.
Okay, this is clear, right?
Yes, sir.
And same is true for S square.
Yes, sir.
Okay, so now what I'm doing is that simply I am expressing L dot S here in terms of J square, L square, and S square, and I am just substituting these eigenvalues here. So
Okay, sir,
J
got
square,
it.
I got it, right?
Yes,
okay.
sir.
Good, very good. Okay, so I will get this particular expression, that will be L dot S is expressed in terms of these three quantum numbers L, S, and J. Okay, Now in this case, of course, S equal to half. So I mean that gives us one advantage because we can get this value of S times S plus 1. Now meanwhile the expectation value of 1 by R cube. So you have to see this problem 6.35c is this one 1 by R cube. The expectation value of that quantity will be 1 by L times L plus half times L plus 1 times N cube and A cube. Okay. So you please look at this problem 6.35c in Griffith's book. I hope this is either solved here or probably some steps will be given, so you can simply derive this thing. So please do this homework. Okay. So why are we requiring the expectation value of 1 by R cube? Because if you look at the Hamiltonian here, so here I have, you see, E square and pi epsilon naught m square c square. So these are all constants. We don't care much because anyway they will come out of any type of bracket. Here I have 1 by R cube and S dot L. So S dot L I can express now in terms of L, S, and J, these three quantum numbers. So I got an expression for that. Only 1 by R cube is something which I need to evaluate. Okay. So that is why here we are looking for the expectation value of 1 by R cube. So that will be equal to 1 by L plus L times L plus half times L plus 1 times N cube A cube. Is this clear? Okay. So you see there this H prime was equal to some constant times L dot S times 1 by R cube, right? Now, if I want to find out the expectation value of this, or let's say the energy that is coming out because of this correction, then what I have to do that I have to take an expectation value of this entire bracketed quantity, right? Let's say some psi, again some psi, right? Okay, right. So here constant will come out. Okay, L dot S I have already got in terms of J, L, S. Now the only thing that is coming out is 1 by R cube, which was left out. Okay, so now I am getting this value also. So that is why I am now able to finally get the complete expression for the energy correction. Okay, I hope this is clear. If you have any question, please ask me. Okay. Okay. So now if I substitute all these values, then I will get this complete expression. That is spin orbit coupling is basically the expectation value of this, and I am putting all earlier slide, and then the complete expression will be equal to, so ESO1, that is the first order correction, equals to E divided by 8 pi epsilon naught times 1 by m square c square times h cross square by 2, and within the bracket I have j times j plus 1 minus L times L plus 1 minus 3 by 4. So can anyone tell me where from this factor is coming? Anyone?
Put the value of speed.
Sir, from S from S.
Okay. So basically I had s times s plus 1. Okay. So here it will be half times half plus 1. So half times how much? I think 3 by 2. So that is equal to 3 by 4. Okay. Good. So I have got this expression, and now I can express it in terms of En. What is En? En is the energy eigenvalue of hydrogen atom in the unperturbed system. So this is the result we got from Bohr's formula also. Okay. So here you can see that this m square, c square, e square, all these things are there. So if I do this, then I can re-express ESO1 in this form. ESO1 will be equal to En square divided by mc square, and within the bracket I will have n times j plus 1 minus L times L plus 1 minus 3 by 4 divided by L times L plus half times L plus 1. Okay. Any question? So now you can see that I have got something outside the bracket which has the dimension of energy, that is En square divided by mc square, and within the curly bracket I have everything in terms of n, l, j, these three quantum numbers. Okay. So now what we'll do is that we'll do an order of magnitude estimation. So here, as we know that within this curly bracket, these terms will give me only some numbers that will be, because L, N, they can only take some integer or half integer values, things like that. So effectively, I will not be too much bothered about the contribution from this part. Okay. However, I'll be looking at what is the relative magnitude of this bracketed term. So En is, let's say, the ground state energy, or let's say the few excited state energy of hydrogen atom wave functions, or 1s, 2s orbitals, things like that. So typically they are of the order of 10 electron volt. Okay. And mc square, if we do this calculation, then we'll get the value that will be of the order of 500,000 electron volt. So effectively, if I take this ratio further, then I'll get something like 100 divided by 500,000. So even if it cancels, so it will be at least of the order of 10 to the power minus 4. Okay. So you can still see here that the correction term that is arising because of spin orbit coupling is also very low in magnitude compared to the actual energy eigenvalues that are present in the hydrogen atom system. Is this part clear to everyone?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, very good. Gulbir, are you here?
Hello, sir.
Acha, tell me, where from I am getting this value of 10 electron volt? You see this value of 10 electron volt, right? Can you tell me where is this coming from?
Hydrogen atom energy.
Hydrogen atom what? Okay. Anyone else can answer this? Pranit?
Sir, here we just take a rough
Sir, yeah.
approximation of ground state and hydrogen atom.
Okay. Okay. So as you know that this goes as minus 13.6 divided by n square, something like that, right? So if n equal to 1, this will be of the order of minus 13.6 eV, right? N equal to 2, so this will be I think 4 or 5 electron volt. So roughly we can say this is of the order of 10 eV. Okay. Okay. Very good. So now, so Pranit, are you here?
Yes, sir.
Can you hear me?
Yes, sir.
Okay. So now tell me, where from I am getting the value of 500,000?
Sir, when we solve for mc square in terms of electron volts, so we will get 500,000.
How will I solve it?
So
M
we can write
square.
the mass
What
of
is M?
Yeah. So mass of
How much is
electron.
it?
Sir, in kg it is 9.1 into 10 power minus 31.
Wait a second. 10 to the power minus 31. So that is kg
Yes.
times c square. What is c square?
So speed of light, 3 into 10 raised to 8.
So this is speed of light in which medium?
Vacuum.
Vacuum, right? Okay. So what will be the unit of this? So this is I
Meter per
think
second.
meter per second. So what will be the total unit of this?
So
Quantity.
this is so energy.
Yes.
Kg meter square. kg
So,
meter square per second square.
kg meter square per second square. Is there any simplified unit
The
to
joule.
express joule? Right. Okay. But are you working in this unit here?
No, sir. Sir, we have to convert it into EV.
How will you do it?
Sir, 1 joule is 1.6 into 10 power minus 19 EV. So we multiply by that. Not multiply, divide.
Okay. Okay. Very good. Okay.
Yeah.
So 1 joule will be certain EV. So you have to divide
Yes,
it
sir.
by this. Okay.
Yes.
Okay. Very good. I actually wanted to check if you are still familiar with this thing. Okay. So this is very simple. If you don't remember how to convert from joule to electron volt, just keep in mind that 1 electron volt means that how much the energy 1 electron is having if we convert it into volt, or let's say in the presence of 1 volt voltage, how much energy an electron can generate. Okay, so it will be basically the electronic charge times 1 volt. Okay, so you know already this is how much, 1.6 times 10 to the power how much,
So
minus
19
19
minus 19. What is the unit?
joule.
Coulomb.
Joule.
Coulomb.
Charge has unit of
Yeah, Coulomb.
coulomb.
Yes.
Okay, times 1 volt. Okay, so you can simply also extract this information from here also. Okay, very good. Okay, so now that is how we are doing this thing. So this kind of exercise is also quite relevant in other courses also. For example, if you just want to know what is the order of magnitude of certain energy term which is associated with some effect, then you can quickly do this thing. So just keep these terms in mind, that this much joule will be equal to this much electron volt. Like let's say 1000 electron volt will be how many joules, or let's say 100 joule will be equal to how much electron volt. Just keep some mind, estimation in your mind, so that you can roughly have a order of magnitude estimation whenever you require, without doing the actual calculation. So now we have got the expression for the spin orbit coupling, whatever energy correction that we are getting from here. Now, what it says here after that is that it is remarkable, considering that totally different physical mechanisms involved, that the relativistic correction and the spin orbit coupling are of the same order of magnitude. Okay, so if you remember that when we estimated the order of magnitude of the energy term that is coming up from relativistic correction, we also have got a similar type of correction, or basically similar order of magnitude from that effect also. So here also we are getting of the same order, that is En square divided by mc square. So if I add them together, then we will get a complete fine structure formula. So again, there is a problem 6.17. Okay, the book is EFITS. So if I add them, then I will end up with this expression: EFS1 will be equal to En square divided by 2mc square times, in the bracket 3 minus 4n divided by j plus half. So this is the addition of both the relativistic correction and spin orbit coupling. I hope this is clear. Okay, very good. So is there any question so far on this? So now here there is an interesting part which we have actually missed. So if you look at this expression 6.65, then you can see that this expression is valid for most of the values of L and J and N. However, something special happens when L will be equal to 0. So if we simply plug in L equal to 0 in this expression, you can see that I have j times j plus 1 within the bracket minus L times L plus 1 minus 3 by 4. Okay. Now what is j? J is nothing other than L plus actually S. So if L equal to 0, then this j will be replaced by S, right? Which is half for the present case. Okay. So the numerator will be S times S plus 1 minus L times L plus 1 minus 3 by 4. Now S times S plus 1, we have already seen this value will be equal to 3 by 4. So here the numerator will be 3 by 4 minus L times L plus 1 minus 3 by 4. So these are cancelling and L is 0 anyway. Okay. So actually this term will be equal to 0. Okay. For L equal to 0. Is this part clear?
Understand that we need to.
The denominator will be also 0.
Right. Denominator will also be 0. But numerator is 0. That is clear, right?
So in the simplification, why can't we cancel L plus 1 from numerator denominator to both?
Okay, see, we can do that, but when we know the actual value, see, there is a difference between this case. Let's say 2 by 2, okay, and 0 by 0, right? You understood what I'm saying?
Yes, sir.
If the numerator is non-zero and denominator is non-zero, so that is one type of case. And here, if you have this one 0 and that one is 0, then the answer is not the same like this one before, right? So there is a difference between this case. So in one case, it will be 1. In other case, it will be undefined. Right?
Yes, sir.
Okay. So here the term in the denominator, if I put L equal to 0 also, then also this term will be 0 because I am multiplying here by L to this complete term. So 0 times whatever you multiply will be 0. So effectively, what I'm ending up for L equal to 0 is a term like 0 by 0. Is this part clear to everyone? Okay.
Yes, sir.
So here it says that for L equal to 0, this expression will be 0 by 0. That means it is not determined or undetermined. So this is a very special case which is called as Darwin term. So in order to deal with this specific case, that is for L equal to 0, the expression for the Hamiltonian, that is the spin orbit coupling term, has been modified, and here we have to include a delta function here, the origin of which can be traced back to Dirac equation. So since here we are not going to discuss Dirac equation in details, because here these things are only explained, kind of the syllabus only considers the elementary discussions on these things. So we will not get into the detailed derivation. However, if any of you are interested, then you can look at the book of Ramstein, and there actually you can see that this is in appendix 7.63, page number 1028. Okay, so it's actually in appendix 7. That is towards the end of the book. So after all the chapters are finished, you can see there is something called as appendix. So it is not human appendix. Okay. So there you can find the exact derivation of this thing. So if you are interested, you can look back and you will see why this delta function is coming into picture. We will not do the derivation here. We will simply go with the expression. So for this special case, you have to take into account this particular form of the Hamiltonian that will give you the energy eigenvalue, that is E3 prime. Okay. Now, although individual terms are not valid at L equal to 0, but total EFS prime is correct for L equal to 0. Okay, so the expression that we have got, it still stays valid somehow for L equal to 0. But if we only want to deal with this term here, H3 prime, then we have to take into account the delta function. So this is called as Darwin term, also Darwin correction. Any question on this? Okay, so what I wanted to mean here is that although individual terms are not valid at L equal to 0, but total EFS prime is correct for L equal to 0. The reason is simple. See here, the total correction term that we have got here, that is EFS1, that is En square divided by 2mc square, and within the bracket we have 3 minus 4n divided by j plus 1. Okay. So this expression is a total sum of ESO prime and the relativistic correction. So here we see that even for L equal to 0, this expression will not have any major impact, or it will not reach this particular case of 0 by 0 kind of form. Okay. However, if we are only looking at the spin orbit coupling correction term separately, then this undetermined situation will appear for L equal to 0. Okay. So the total correction will not be impacted. However, the individual term will be affected for this specific scenario. Any question? Okay. So please go and look back if you are interested in learning more on this thing. So now what we will do is that we'll look into the energy level diagram of hydrogen atom and what is the effect of fine structure on these energy levels, or let's say whatever will be the spectra that will be generating as a result of that. Okay. So if you remember that earlier when we have discussed about the spectra of hydrogen atom, we talked about only the principal quantum number, that is n equal to 1, n equal to 2, n equal to 3, things like that. Okay. And for each of these energy levels, we have certain specific energy that is determined by the principal quantum number. And whenever there is a jump between n equal to 2 to n equal to 1, or n equal to 3 to n equal to 1, n equal to 4 to n equal to 1, so depending on the type of transition, we will have different kind of spectral lines which comes within the different frequency range of electromagnetic spectrum. Some will be within UV region, some will be within IR region, some will be within the visible region of optical spectrum that we have already seen. So there fine structure was not included. So that is the case for Balmer series, Passenbach series, Passen series, things like that. Now we are interested in including the correction terms that is arising from the fine structure. So let us look at. Let's say if we look at the ground state, there is n equal to 1. So here I have L equal to 0. That is only possible because the L value that is possible for n equal to 1 will be 0 to n minus 1. So here n equal to 1. So the only L value that is possible for n equal to 0, n equal to 1 state is 0. Okay. So here I will only get this S term. L equal to 1, L equal to 2, L equal to 3. These are absent. Okay. So by the way, I hope you are familiar with these different notations. So if L equal to 0, these are in spectroscopic notation. This is called as a S term. If L equal to 1, this is called as a P term. L equal to 2, this is called as a D term. L equal to 3, this is called as a F term. Okay. So I hope you are already familiar with this thing. Now if we look at the n equal to 2 energy level, then the possible values of L are 0 and 1. So here I get S term, and here for L equal to 1, I get the P term. Okay. Okay. However, if I take into account the contribution of spin, then the possible values of J will be L plus minus S. That means L plus half to L minus half, which means that the values that will be possible here will be 3 by 2 and half. Is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
So basically my J is coming from L equal to S to L minus S. Okay. So here I have only up to L equal to 1 term that is possible here. Now if I look at N equal to 3, then here I have L equal to 0. For L equal to 1, I have two possible values of J that are possible, which are 3 by 2 and half. And for L equal to 2, the values of J that are possible will be 5 by 2 and 3 by 2. So you can simply do the calculation and you can look at this thing. Okay. Now if I go to N equal to 4, then I can have here L equal to 0 and then L equal to 1 and then L equal to 2. So here also the values of J that are possible are 3 by 2 and half. For L equal to 2, they will be 5 by 2 and 3 by 2. And for L equal to 3, the values of J that are possible are L 7 by 2 and 5 by 2. Okay. So now, if we combine all these things and if we want to look at what are the total, let's say, lines that are arising as a result of this fine structure constant, then we have to take into account what are the possible values of J that are arising from different values of L. Okay. So now here if I look at N equal to 1, then the only value of J that is possible is J equal to half, because only one L is here, S equal to half, so J will be half. Okay. For N equal to 2, I have two different values of J that are possible. One is 3 by 2, other is half. For N equal to 3, I have three different values of J that are possible. So one is 5 by 2, which is basically here, then 3 by 2, which is also here, and J equal to half, which is coming from here. Okay, remember 3 by 2 is also here, but since we are only taking one, I mean the value of J once, so we can take it from any one of them, but we're just looking at what are the possible values of J that are associated with one particular value of N. And for the case of N equal to 4, we have four different values of J that are possible, which are J equal to 7 by 2, J equal to 5 by 2, J equal to 3 by 2, and J equal to half. Okay. So is there any question on this so far? So is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. So now, as you see that earlier we are only dealing with the principal quantum numbers when we were explaining the spectra. However, as a result of the fine structure splitting, these levels are further splitted into different J values, or let's say the splitted levels are associated with certain J values. So if we want to know the transition, or let's say the fine structure spectra that is arising in such cases, then what you have to do is that you have to look at the transition between these separate J levels, and that will be determined also by the selection rules which are in place. So we'll look into this. Now, before going that, so I hope up to this there is no question. If you have, please ask me. Okay. So if not, then I'll go to the next part. So first thing is that, so we have got the total correction term here on this slide, that is EFS1 equal to En square divided by 2mc square, and this term within the bracket, that is expression 6.66. Okay. Now, if I want to know what is the total value of energy after including all these corrections, then what we will do is that we will take the energy eigenvalue that is coming up from the Bohr's formula, that is minus 13.6 divided by n square. So this is this term, and then these two correction terms. So one is coming from the relativistic effect, other is coming from the spin orbit coupling. So we have a total total number of three terms here, and the total energy eigenvalue, which is no longer denoted by n only, rather there is also a J which is associated with it, because you can see J is determining subsequent splitting of this n. So then we have to take into account all these three terms. Okay. So here there is some discussion which is written that what is a good quantum number and not a good quantum number. You can read this thing. However, the thing which we are interested in is that the total energy level will have the contribution from all these three terms. Okay. So now we can actually express the term shift, but before that, let us actually go and look at how different spectroscopic terms are denoted. So you have probably come across this thing earlier. So let's say in spectroscopy, whenever we are talking about a particular energy level, so this energy level can come up or arise because of different effects. And different effects are also characterized by different quantum numbers. So typically, these are the three quantum numbers which we deal with: S, L, and J. What is S? S is the spin quantum number, L is the orbital angular momentum quantum number, and J is the total angular momentum quantum number. Okay. Now the general, so using the combination of all these three, I can make a unique way of representing any specific energy level. So this is called a spectroscopic term. So this term actually represents any kind of energy value. Okay, or let's say an energy level. Okay. So the general form of a spectroscopic term is this one, that is, the form is standardized in this format, which is 2s plus 1 Lj. Okay, so S is spin, L is the orbital angular momentum, and J is the total angular momentum. Now, here S and J will have values that we will be using. However, L will put some symbol depending on what is the value of L. So let's say if L equal to 0, the corresponding term symbol will be S. If L equal to 1, the corresponding term symbol will be P. If L equal to 2, it will be D, and if L equal to 3, it will be represented by this term called as F. So let us look at a simple example. Suppose S equal to half, L equal to 0, so then J will be L plus S, which is basically half. So if I want to represent the spectroscopic term, basically that particular energy level through a spectroscopic term, then the term symbol will be 2s plus 1, that is 2 times half plus 1, and then L is 0, which means that it will be S term. So it will be S and J is half, so half. So this particular spectroscopic term will be 2s half. I hope this is clear, right?
Yes, sir.
Okay.
Yes, sir.
Okay. So now tell me, if S is 3 by 2, L equal to 1. Okay. So what will be the spectroscopic term or terms? Okay, let's make it simple. Let's make it half actually. Then it will be a little bit easier. Anyone?
It will be 3s 3 by 2.
Okay, first tell me what will be the value of J?
So J will be 3 by 2.
Okay, J can also have half value. Okay, but let's go
Yes,
with
sir.
3 by 2. Okay, so now tell me what is 2s plus 1? That is 2 times half
Plus 1, it will be 2.
plus 1. L is 1, which means that it will be P term. Okay, and J is 3 by 2. So this will be 2P
3.
3 by 2. Okay, if J is half, then we will have another term. This will be 2P half. Okay, so this is clear, I hope. Okay, so any questions so far? If not, then we'll finish the class today here. So in the next class, we'll talk about our different spectroscopic terms that are arising from this fine structure splitting. So we are finishing it here. Okay.
Thank you, sir.